The title of this presentation is Poisson Structures and Yang-Baxter Algebras of the Four-Vertex Model and Higher Spin XXX Chain. To begin with the presentation overview, I'll be drawing the attention of the viewer to some previous work that I did earlier in the year, in which I'm just going to reproduce a couple of the slides from a previous work on the 20-vertex model with the overall aim of discussing connections between the 6-vertex, 20-vertex, and 4-vertex models. And although when one may be looking at different types of vertex models from statistical physics or statistical mechanics, whatever you want to call it, they may have differences, namely in the dimensionality of the underlying state space in which the models are defined, or even possibly the total number of configurations in the state space. And in particular, from an upcoming work that I thought it would be coming up soon this week, but sometimes it takes the archive a little longer to process my papers because my papers are all single authored. I'm pretty much drawing connections with some previous work that I did with the 20 vertex model and the 6 vertex model. In the first work that I did in the 6 vertex model, I was talking about different types of ways that you can make sense of integrability and exact solvability for that model. And then when you're looking at the 20 vertex model, which is a three-dimensional generalization of the 6 vertex model, you can encode domain wall boundary conditions in a very similar manner, from which you can infer some weakened form of integrability that still is a byproduct of the quantum inverse scattering method. And what I want to report on in this type of presentation, this brief presentation, is that there can be some similar further application of the quantum inverse scattering method for the 4-vertex model. And there are different types of implications or consequences of making use of this model from box plane partitions or other combinatorial interpretations or aspects which are of interest for further investigation. So, as I've been talking about, as in the second bullet point of this overview, we want to introduce from a very general method or very general level some of the previous motivations of the author, me, through investigations of the quantum inverse scattering method. And by and large, I've done a series of presentations for the 20 vertex model also on the channel, in which I discuss and draw the attention of the viewer to different applications of this framework and where it comes from, in which it's an adaptation of seminal work from Padiv and Takachan, in which they studied Hamiltonian methods in the or Hamiltonian methods, I think, in the theory of solitons, I think was the name of the official reference. And it came up in a paper that I read, in which from a paper due to from a paper of Koya Reshetikin and two of his students, Anand Shah and David Keating, they mentioned in the last sentence of their paper from integrability of limit shapes, of inhomogeneous limit shapes for the 6 vertex model, that it would be of interest to study integrability in other types of instances, maybe integrability of a Hamiltonian flow from integrability of inhomogeneous limit shapes. So I'm very much here to report upon what types of notions of integrability can we salvage for vertex models and what that would actually relate to some work that I've already previously done that's been on the archive for a while, some of it like around a year for the paper of the 6 vertex model and the 20 vertex model earlier this year, I think in June or July, I posted it, and how that would actually relate to a different type of vertex model that's also lower dimensional, namely 2-dimensional like the 6 vertex model, but having 2 less configurations, which I'll motivate and further explain later on in the presentation. And central to the quantum inverse scattering method, or QISM, this is allowing us to further understand the transfer matrix, the quantum monodromy matrix, and closely related objects, and more or less Poisson structure and Yang-Baxter algebras, they come into play because the Poisson structure is coming from the fact that you can look at different types of Poisson brackets that you have to compute and asymptotically approximate as the finite volume of some type of region over the square lattice for the 6 vertex model, or the triangular lattice for the 20 vertex model, is taken to infinity, in which pretty much your finite volume is becoming almost as large as the infinite volume of the entire underlying lattice, whether it be the triangular lattice or the square lattice, over which you're looking interactions, over which you're trying to study interactions, whether long-range interactions or short-range interactions in your system. And all of these objects together, they're very important because they help us establish whether there are any types of combinatorial consequences I had alluded to, or maybe even algebraic consequences, because for the 6 vertex model and the 20 vertex model, which I'm going to introduce and motivate a little for the viewer before I briefly mention how a lot of this methodology and a lot of this machinery can also hold water and be of significance and consequence for the 4 vertex model. You pretty much have to make use of a lot of identities or a lot of identities with the Poisson bracket for the transfer matrix and the quantum monodromy matrix, and how that's ultimately relying to the vertex model that you're starting out by defining a probability measure with. So without much more delay, I'm going to just define the 6 vertex model. This is just kind of a rehashing of a previous presentation of bits and pieces of a previous presentation that I'd given, 2 months ago or 2.5 months ago on the channel, that I just wanted to refresh and reiterate because it's pretty much demonstrating how you can look at notions of universality, especially maybe whether there are any similar notions of integrability, as well as relating to other types of characteristics from the fundamental objects that you're using for the quantum inverse scattering method, like I'd mentioned and alluded to in the previous slide, namely the transfer matrix and the quantum monodromy matrix, and how this essentially relates to approximation of operators from a block representation of the transfer matrix and the quantum monodromy matrix, which can then be equivalently phrased as computations with the Poisson bracket of these operators. But before we get to more of those details, the 6 vertex model, it's a classical model of statistical physics and is given by the fact that each one of these configurations from the sample space of 6 possibilities has a satisfaction of the ice rule. The ice rule is given by the fact that about every vertex in the square lattice, there are 2 ingoing arrows and 2 outgoing arrows. But besides the orientation of the arrows, there's also another object that's of fundamental interest, which is called the height function, which is given, informally speaking, without me defining anything, but just speaking about it, because I feel like that's probably easier to understand in the first place, is that it's given by a graph homomorphism from the faces of the square lattice into the integers. And the integers is given by the fact that if we fix the image of the graph homomorphism in this uppermost left face of the quadrant to be 0, when we pass an arrow that's directed away or pointing upwards, which is directed away from the vertex in the square lattice, the height function decreases by 1, or it can either increase by 1. So we can see that there's a natural way in which the image of the height function from the image of the graph homomorphism along each one of the faces of the square lattice can either increase by 1 or decrease by 1, which is pretty much a universal characteristic of the height function for any vertex model, whether it be also the height functions for the 20 vertex model, which in one of my papers on weak integrability of the 20 vertex model, I alluded to and discussed as triangular height functions, or even a height function of the 4 vertex model, which is also defined over the square lattice. And from these 6 possible configurations, we can either have a way to represent them in terms of, as I alluded to and as I had introduced, the image of the graph homomorphism along each one of the faces, or even a line configuration, which is given by each one of these possible configurations are given below it, which is adapted from the paper that I had alluded to from Keating, Reshetikin, and Sridhar, in which they also provide line configurations. And a line configuration is really much for the 6 vertex model, it's pretty much nothing more than a way to visualize whether you would actually shade some lines dark or white, black or white, depending upon the orientation of the arrows amongst or surrounding the vicinity of each one of the vertices in the square lattice that you're looking at. And having these different types of ways to visualize and to think about different types of configurations which are coming for the 6 vertex model, it's really great to have into mind, because there are different types of papers in the literature which each have their own type of preferred convention in terms of demonstrating or providing some type of illustration or visualization of large macroscopic scale configurations of the 6 vertex model that one can study. And in the next slide, in terms of defining a probability measure, what we do in probability theory and statistical physics is that we're always looking at some fixed boundary condition C, which pretty much I would say, obviously not in all papers of the literature, but probably in the vast majority, most people would consider domain wall boundary conditions for the 6 vertex and the 20 vertex model. That's not to say that that's always the types of boundary conditions I've considered in my work. I've also considered slope boundary conditions in another older paper around like more than 2 years ago on the 6 vertex model, in which I was studying logarithmic delocalization of the height function. But in the case for the quantum inverse scattering method and framework, what we'll always want to do is fix domain wall boundary conditions, which is meaning that on the left-hand side and the right-hand side of the finite volume over the square lattice over which you want to study macroscopic configurations of the 6 vertex model, the arrows are pointing inwards, which is meaning that we're restricting half of the orientation of the configuration that's appearing that has a non-empty intersection with the boundary of the finite volume to be pointing inwards, whereas the top and bottom portions of the configuration are pointing outwards, so meaning one's up and one's down. So this is really a way in which boundary conditions play a pivotal role in terms of the quantum inverse scattering method, and there's very much a similar way to introduce 20 vertex boundary conditions, domain wall boundary conditions, that is, in addition to fixing boundary conditions, which are also coming into play for the 4 vertex model, in which you can pretty much look at similar types of boundary conditions, even if the underlying dimensionality of the state space, like I had alluded to, of the vertex model is either different or there can be some difference in the total number of possible configurations that you can have in whatever vertex model you're interested in studying. And specifically, the probability measure is given by a weight function, a W of omega normalized by the partition function. And this probability measure and the partition function, which are normalizing the weight so that this ratio is a probability measure, namely this the image of any configuration of the under the probability measures strictly contained between or is contained between 0 and 1. It takes the form of A1 to the N1, A2 to the N2, B1 to the N3, B2 to the N4, C1 to the N5, and C2 to the N6, where these A1, A2 terms are given by the number of arrows which are of type 1 and type 2 respectively, as well as type 3 and type 4 corresponding to N3 and N4, and finally type 5 and type 6 corresponding to the last two factors which are given in the weight function. And as I mentioned before, for the 6 vertex model, the partition function is dependent upon both the configuration that you're looking at, as well as the entire sample space of the vertex model, which is given by the second parameter dependency of big omega. And we just suppress these parameters because pretty much it's very obvious that the partition function should be dependent upon a summation over all configurations in the sample space of the torus of the weight function W of omega. But rather than defining the probability measure and the weight function, oftentimes in statistical physics, there can introduce a simplification to the terms that appear in the weight function for the 6 vertex model, much like there can also be for the 20 vertex model, or even in some cases for the 4 vertex model, which is consisting of an isotropic parameter choice, which is given by setting A1 and A2 equal to A, B1 and B2 equal to B, and C1 and C2 equal to C. And from these 3 common isotropic parameters, A, B, and C, you can form a weight function, which is given by A to the N1 plus N2, B to the N3 plus N4, and C to the N5 plus N6. So sometimes having this type of simplification, it can come into mind because it's going to inform the type of probability measure and the type of weight function, which we're going to normalize by the partition function of the 4 vertex model. And in particular, what's going to end up happening is that we're just going to ignore the B term, which is appearing in the weight function for the 6 vertex model, which is just going to result in a vertex model with two less configurations than the 6 vertex model, hence the 4 vertex model that we can then make use of and we can study from, or that's very amenable to the quantum inverse scattering method. But besides the isotropic parameter choice, which very much is a very classical feature of the 6 vertex model that a lot of people study and that a lot of people have made use of, there's also an alternative parameterization of the weights for the 6 vertex model that we had introduced, which is very much coming into play in terms of the quantum inverse scattering method, which was originally introduced, I believe, probably even maybe earlier, but the first time that I saw it was in terms of the paper due to Keating, Reshetikhin, and Sridhar that I've been mentioning even across other playlists in my channel for the 20 vertex model, in which they look at a way to parameterize the weights of the 6 vertex model in terms of two external fields, H and V. It's pretty much like the electric field and the magnetic field from physics. But the point is that when you're coupling the weights or when you're parameterizing the weights in terms of these two external fields, you can introduce another way or another dependency of the isotropic parameters in each one of the weights, in which, for instance, you can look at the exponential of the sum of these two external fields multiplied by A, which you can set for one of the parameters, as well as for A2, you can look at A times the exponential of subtracting two of the external fields. Or for B1, you can look at subtracting the second external field from the first external field. Or for B2, you can look in terms of taking the second external field and subtracting the first external field from the second external field. And then for the last two parameters, which represent possibilities for the weight function of the 6 vertex model, you can set them equal to either C lambda or C to the reciprocal of lambda, where lambda is some parameter that's greater than or equal to 1. So again, this is just really a way to make ourselves comfortable in terms of what's the total number of configurations for the 6 vertex model, because probably that's the most famous vertex model out of them all that was really studied thoroughly from a seminal paper from Lieb in the 1970s, I believe, if I have the date correctly, in which he computed the residual free entropy of the torus under an isotropic parameter choice, in which he set all of the isotropic parameters A, B, and C to be equal to 1. And this is a seminal paper because it's really demonstrating how you can have some type of non-trivial consequence for the free energy of some vertex model under a very simplified assumption of the parameters, namely the isotropic parameters all being set to 1. And that's really what a lot of people can find appealing about statistical physics or statistical mechanics, is that a lot of times it may seem like so simple that it may even be counterintuitive, but this is really a way in which then, if we have some type of information about the behavior, namely the free energy of some vertex model under a very narrow and restrictive range of parameters, the isotropic parameters, which are going into play from the weight function of the 6 vertex model, then we can really start and try and hope and aspire to be more ambitious in terms of what types of other dependencies of the free energy or other types of thermodynamic quantities will we expect to hold weight or to happen for a vertex model when we're looking at the thermodynamic limit in a weak infinite volume limit to infinity. And again, like we've been mentioning in previous works of the author, I was able to answer and resolve a conjecture about integrability of the Hamiltonian flow from information on integrability of inhomogeneous limit shapes due to Keating, Reshetikhin, and Sridhar from several computations with the Poisson bracket. And pretty much you make use of different types of computation with the Poisson brackets because they pretty much come in two flavors. They either come in one flavor in which you look at the Poisson bracket, which is given by the first item of f and g. F and g just represent two test functions, and you're just integrating over some compact interval from negative L to L, and you're multiplying by some imaginary prefactor, as well as given by the fact that you're multiplying derivatives with respect to psi or psi bar. And I haven't defined and formally introduced psi and psi bar, but just it's a solution to the nonlinear Schrodinger's equation. So it's fundamentally rooted in some type of physical interpretation or some type of physical reality about how there's a constraint about how much we can gather simultaneously in terms of measurements and information from the position of momenta of particles in quantum mechanical systems. But besides this, below it, you can also look at the Poisson bracket of a tensor product, which is given by just a similar type of accompanying expression from the Poisson bracket of these two test functions, f and g, that's given in the first slide, just given by the fact that instead of ordinary multiplication, when you're taking the Poisson bracket of a tensor product, you insert a tensor product in the place of ordinary multiplication from each one of the derivatives. So it's pretty much a same type of way to be able to define a tensorization of the Poisson bracket between two test functions. And now I'm really going to introduce the 20 vertex model because more than anything, I've really been trying to exhibit in this presentation that there's a lot of similarities between different types of vertex models, and that even if you start maybe with integrability, you can look at which types of consequences of an argument would hold for the 20 vertex model or even the 4 vertex model. So I'm pretty much demonstrating how you can kind of have a tour de force, I guess, if that's the right expression from like French people or other type of people in the world, in which you can start from one vertex model and you can really gather information about maybe how the underlying state space, dimensionality of the state space, as well as in addition to the fact about how the total number of configurations would change, how you could still be able to glean or to make some similar type of conclusion. And this is given by the fact that for the 20 vertex model from a paper due to DiFrancesco, which has similar work or seminal work on combinatorial aspects as well as determinantal representations and determinantal point processes of the partition function, you can look at a way to group together into 6 categories like we did for the 6 vertex model, but instead for the 20 vertex model, in which, as I've alluded to and described in other types of presentations I've given on playlists on the channel, you can look at ways to construct and group configurations into categories W0, W1, W2, W3, all up to W6, in which if you look in the first column for W0, these types of 2 configurations that are paired together that have the same statistical weight and the probability measure that one can define for the 6 vertex model in the same type of way that you can define a probability measure that I had provided earlier for the viewer for the 6 vertex model. It's pretty much given by the fact that you either have all of the arrows pointing inwards or all the arrows pointing outwards, because this is a 3-dimensional generalization of the ice rule. Because remember, the ice rule over the square lattice is given by the fact that you can have 2 arrows pointing in and 2 arrows pointing out. And for the 20 vertex model, it's instead either 3 arrows pointing in or 3 arrows pointing out. And then if you look in the next column of configurations that have weight W1, you can either have a very similar type of arrangement in which this middle line is colored solid, whereas the rest of the lines that are incident to this vertex in the triangular lattice are colored white. But then in the corresponding complementary type of configuration that has the same statistical weight, you can have these types of vertices in these lines that are incident being colored black, whereas that middle center line, which was colored black or was colored dark in the previous configuration on top, is instead colored white. So you can kind of think about how those line configurations that I exhibited and that I provided for you for the 6 vertex model in the previous slide, they really come into play because it's a great way to visualize different ways in which you can color lines or portions or permutations or different subspaces of the triangular lattice, which is coming into play from, you can see the configurations W2, you can see with my mouse how these 2 are colored black and this is colored white, and so on and so forth for the remaining configurations in the sample space of the 20 vertex model. And again, from DiFrancesco's paper, this is just really to hit home or really to emphasize that there's just a lot of different ways to be able to highlight or be able to visually represent either through ingoing or outgoing arrows or either coloring lines of the triangular lattice, which are comprising and constituting 20 vertex configurations, which are ultimately feeding into the definition of the probability measure for the 6 vertex and the 20 vertex model as either being defined over the square lattice or over the triangular lattice. And now I wanted to get more to the 4 vertex model, in which I just wanted to, in a few slides, just really exhibit how you can have a very clear idea about how one would be able to apply the quantum inverse scattering method under some appropriate ranges of bound or some appropriate classes of boundary conditions, and how that would relate to all of the comments that I had been introducing previously for the 6 vertex model and the 20 vertex model. And that's to say is that the probability measure is given by a very similar expression just by the weight of the 4 vertex model instead of the 6 vertex model, in addition to the fact that you're normalizing by the partition function of the 4 vertex model. Furthermore, as I had alluded to previously earlier in the presentation, you can form the weight of the 4 vertex model from the weight of the 6 vertex model by excluding the B factor, which has the effect of narrowing down or whittling down the total number of configurations in the sample space of the 6 vertex model by 2, so that you get the configurations of the 4 vertex model, which is also supported over the square lattice. And in particular, from a 2007 work that I've been discussing a bit in the preprint that's going to come out due to Bogol-Lyubov, he talks about a representation for the partition function of the six vertex model in which you can introduce some similar type of isotropic parameters corresponding to the weights WA, WB, and WC. And then before you actually exclude the B parameter, which is one of the factors that appears in the weight function for the six vertex model that doesn't appear in the 20 vertex model, or sorry, in the four vertex model, you can express this partition function, which is very helpful in terms of a summation of the configurations over the sample space for the four vertex model from a product over negative integers as well as a product over positive integers of these three weight factors, WA, WB, and WC. And in general, from more of a philosophical point of view, this obviously isn't the only representation that one can have for the partition function of a vertex model. In another paper that I did in this year, after the paper in which I looked at quantum inverse scattering for the 20 vertex model up to Dinka and automorphism and established a lot of connections between three-dimensional Poisson structure, weak integrability, and triangular height functions, there are really even other types of ways in which you can look at making use of a determinantal representation for the partition function of the 20 vertex model. So it's really just going to show how much of a rich literature there is and how much of a diverse background there is from several types of authors in the field who have made seminal contributions, in which you can either look at some determinantal representation of a partition function for the vertex model of interest, or you can draw more of the interest towards maybe correlations in the emptiness formation probability or even the quantum inverse scattering method. And the four vertex model, as I've been mentioning in this 2007 work that I've been alluding to due to Bogolyubov, he provides a representation for the L operator, and the L operator is really great because when you have some representation for the L operator, you can look at several types of computations in terms of taking products of L operators or even taking products of diagonal matrices and R matrices to be able to form some type of representation in the infinite volume limit for the transfer matrix, which can then get you some type of information about the quantum monodromy matrix. And obviously, this is a very technical business and a very technical endeavor because these types of computations, depending upon which particular expansion you want to look at in terms of the transfer matrix and the quantum monodromy matrix, they can be very involved. But in this case, what's really helpful about this particular representation for the L operator of the four vertex model is that much like the L operator of the six vertex model, there is a representation in terms of these sigma n minus and sigma n plus terms, which are given by the Pauli bases, which are given by, in quantum mechanics, 2x2 matrices, which are establishing actions in fundamental physical constraints of the reality that we're in which we're not able to basically gather with infinite precision or infinite probability measurements of the position and momenta of different types of quantum mechanical systems at the same time. So really, this L operator for the four vertex model or the six vertex model or even of the 20 vertex model, which is different from the L operators of the four vertex model and the six vertex models because it has some more type of algebraic characteristic from the fact that there are families of L operators that hold up to Dink and automorphism. It really just goes to show about how rich and how many different types of interpretations or characteristics one can form from the quantum inverse scattering method, like how I've been trying to explore and further investigate in some of my more recent previous works. And it's really helpful also to have into mind these types of connections that I've been mentioning because you can basically infer equalities of the transfer matrix from the six vertex and the 20 vertex models and establish some type of correspondence from equalities from the transfer matrix and the four vertex models. And what that means is that if you have some type of tensor product of the Poisson bracket of t minus x and t minus x of lambda and t minus x of mu, this is exhibiting how you would expect the Poisson bracket to interact when you have two transfer matrices that are given under different spectral parameters. And accordingly, to this, you can also look at t plus of x of lambda and t plus of x of mu, which is just also looking at the plus infinite limit, the limit as n goes to infinity in comparison or in juxtaposition to the limit as n goes to minus infinity of the Poisson bracket of the tensor product. And basically, there are ways in which you can establish some types of analogs to classical identities, which are given in seminal work like I had alluded to due to Fadiv and Takadan, in which in their method, in their paper from the study of Hamiltonian systems, they were in that seminal work, they provide original identities for how the transfer matrix of different types of if I remember correctly, soliton systems would behave, and how you can actually think about making use of matrices for vertex models in terms of these Poisson brackets, and how you can decompose the action of the Poisson bracket from different types of, basically the form of the integral, like I had mentioned earlier, in terms of the integral over minus L with an imaginary perfactor and multiplying by basically a bunch of mixed derivatives that are taken with respect to solutions to the nonlinear Schrodinger's equation. And this is just another type of equality that can be provided, in which I discuss it more in my paper for quantum inverse scattering for the 20 vertex model, in which you can basically, again, look at a way to take the Poisson bracket of the tensor product of the transfer matrices, either as the parameter goes to plus infinity or goes to minus infinity. And altogether, this is to say that the Poisson structure for the four vertex model consists of these types of relations, in which you have four sets of relations, C1, C2, C3, and C4, which can be used to generate the overall Poisson structure, script P, that I call here. And you're basically permuting the spectral parameters. Either you have a spectral parameter U in the first argument that appears in the Poisson bracket, or a spectral parameter U prime, which appears in the second argument of the Poisson bracket. And you're basically able to asymptotically approximate in a weak infinite volume limit what each one of these Poisson brackets would be. And that's pretty much the type of program that I had research program that I had pursued for the 20 vertex model before, in which you just have a larger collection of Poisson brackets that have to be approximated, in spite of the fact that there's some more complicated L operator, which is defined in terms of a tensor over a tensor product of two spaces, in which ultimately also has some quantum mechanical interpretation. And altogether, when you're looking to perform computations with the Poisson bracket, a lot of times it can be helpful to have different types of shortcuts. And what comes into play when you're looking at computing the Poisson bracket, which is ultimately integrating some difference of partial derivatives, is that when you have two arguments in the Poisson bracket, which are just differing dependent upon the spectral parameters, roughly speaking, this is extremely helpful when approximating different types of relations on the Poisson structure for the 4 vertex model, the 6 vertex model, and the 20 vertex model, because you can pretty much if you assume a unit constant, a unit coupling of interaction, basically the reciprocal of U minus U prime, and all these constants come into play from the terms of the Poisson bracket that I approximate in the upcoming preprint. But besides Poisson structure and Yang-Baxter algebras for vertex models, the Yang-Baxter algebra itself can be inferred by the fact that when you have some type of operator representation for different blocks of the transfer matrix, you can look at forming expressions for the Yang-Baxter algebra from these operations, which are ultimately related to computations with different types of L operators. Like I've looked at L operators for the 6 vertex model and the 20 vertex model. And in this presentation, I established to the viewer how the L operator for the 4 vertex model can be established in terms of basis vectors, E sub n, sorry, I think I forgot to say that, but they're basis vectors as well as Pauli matrices and projectors. And this is really ultimately relating to the fact that a primary quantity of interest that I describe in this paper is the support of A of U, B of U, C of U, and D of U, which are each one of the operators which appear in the four components or four constituents of the block representation of the transfer matrix for the 4 vertex model, which you can pretty much look in terms of a span, because overall, I mean, after all, it's something that's defined over the square lattice, so you can establish types of parallels between linear algebra and the types of computations that you're wanting to perform within statistical physics in the quantum inverse scattering method, which is pretty much a span of A n minus 1 of U and so on for all of the remaining operators which are appearing in the block decomposition of the transfer matrix. And from the L operator of the four vertex model, you can also define an L operator of the higher spin XXX chain. And the higher spin XXX chain just differs from maybe another type of XXX chain, or maybe even other types of spin chains I've talked about in my previous preprints on the archive, because it's a higher spin generalization, because it's helpful for us to consider and to take into mind, because there are higher spin generalizations of vertex models in which you can look at more than one particle, in which you can look at more than one particle per vertex of whatever lattice you're defining your interactions over. And I'm not going to go into exact detail, but it's pretty much exactly of the same form of the L operator for the four vertex model. So it's really helpful to have another class of L operators in mind for the higher spin XXX chain in comparison to what we already know for the four vertex model, because you can pretty much map between them, and you can have some representation of the transfer matrix for one vertex model and be able to map over these results from action on the basis elements, from the poly basis elements, which would allow you then to be able to establish some type of product representation, as I'm giving here in the last item on the slide, in terms of T of XX of U, which is namely the transfer matrix of the higher spin XXX chain, which is dependent upon the spectral parameter U, and actually having some block decomposition like I've been alluding to for the four vertex model, which is given by AXX of U, BXX of U, CXX of U, and DXX of U. And finally, to close out with a conclusion, we were discussing connections between the 6 vertex, 20 vertex, and 4 vertex models. And as we had alluded to, we were talking about, from a pretty general level, some previous motivations from my previous works and investigations of the quantum inverse scattering method. And in doing this, we pretty much introduced the transfer matrix, the quantum monodromy matrix, and several other types of related objects, as well as maybe some future interests or future directions of research interests. And thanks for watching.